Hello, peoples. Welcome back to another episode of statistics. This is week 5, lecture 1. The reason I stopped at lecture 1 is because all the way up to week 5, lecture 1, we cover all the things related to kind of the same subject of raw data, continuous, discrete, mean, median, errors, stuff like that, line of best fit. And then after this part, we'll get into more discrete mathematics F styles where we're talking with sets, unions, intersections. So I'm going to split into 2 parts. And so let's head right into it. This part we learned last lecture. I just wanted to point out one thing. So the equation of the least squares line L is given. So remember, this one, this one right here. Let me zoom in. Okay, so this equation, you'll have some graph, well, not graph, you'll have some points, right? And then you'll have the line of best fit goes right through them, okay? The way you calculate A is you get your mean for Y and your mean for X. Your B, you get it through this equation. Not going to go into these equations because I explained them last lecture. But once you get them, you sub in your B and you sub in your A. And after you do that part, whenever you have an X variable and you sub it into X, it will give you the Y value at this line, okay? Which is an estimate, right? You're predicting. Because you have data around that line, you're predicting because this is the best fit, like this is the best case scenario. However, the line doesn't actually have an arrow like I drew. That's wrong. The way it goes is only from the data to the data. It doesn't go past where the data exists. So if the data doesn't exist here, you can't continue the line past this. Okay? So therefore, this question right here, I'll give you a bunch of data. If I give you a number and I tell you, give me an estimate for this number that is not within this data, then you'll say no. Okay, you'll say no, I can't predict that. I can't take this number, plug it into my X, get some value Y, because this function doesn't go infinite. I can only predict numbers that are within my data, like within this sections, because of the line of best fit. The line of best fit doesn't exist past these points. Okay, so that's one thing you got to keep in mind. The other thing here, it says, based on the regression, answer the following question. What is the value of the sample correlation coefficient? So that's Pearson's sample correlation. Oh my God, why am I writing this? It's basically variable R, okay? So we spoke about how to get variable R before, but since you have here, so remember, variable R, you do, I believe, something like SXY over SXX. Don't take me for this, it's in the equation sheet, so make sure you check it. However, if you don't have points and you have something as simple as this, or you have the point B, then you can calculate your B using a little different equation, which is also given in the formula sheet. B equals R times the square root of SXY over the square root of SXX. Okay, and then you can isolate for your R, and so you'll just do B equals, it will be R equals B, and then you flip these, so it will be square root of SXX all over the square root of SXY. Okay, so that's the other way you can find it. This is your B, right? It's right here. So that's the same thing here. And that's how you can get your R. This is another equation to get R, and this is also another equation to get B. Okay, so assessing the fit of the least squares line. If the original line is fitted, blah, blah, blah. Then you have this, which are predicted values. Just like I was saying, we predict it, right? So when I put the graph up here, actually, let me draw another graph. That's a better one on the side. So if this was my graph, and I have points right? So if it was something like this, and I drew the line of best fit, and let's just assume it goes straight into the middle, actually, it just goes between, right? It doesn't exist past the data or before the data. So, whenever you plug in an x value, I will give you a y, which is, let me choose a different color. Whenever I plug in an x value, it will give me a y, which meets right here, right? But the data at this particular x value is actually up here. That is the estimate. But the line of best fit basically gives you the best case scenario. So there is some errors, and that's what we call residuals. And basically the residual is, you can think about it, the distance from the line to the actual point. Like that's your error margin. So to study the relationship between the length of the service call and blah, 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 you have this data. Right here it tells you with the following prediction line. Let's look at the raw data again, specifically at these 2 points. So if you look at this data, point 64 and 4, which would be right here, right? And then 4 and 74, which is right here. So what they're saying is, instead of us looking at the hard data, how about this? Let's say I only have my x, which is 4 units. Is that the x in this case? Well, I would say minutes. Time is usually the x because it's the independent. So I'm going to use x as my time. And so what I'm going to do here is I'm going to take my, well, actually the way they wrote it, this is x and this is y. So I guess we'll just use that. So I'll take my 4 and I'll plug it in here. Assuming I don't have the 64, I want to predict, right? So it'll be 4.162 plus 15.509 times 4. So I'm going to plug that into my beautiful calculator. And what do I get? 4.162 plus 15.509 times 4. And I got 66.198. Now, why is this number different from this number? And basically, that's because, like I said, that is an estimate, which gave me the point at the line. Wow, this is, let's say, 64. This turned out to be 66. And you see, that is the error margin. And so what they're telling you here, therefore, the n residuals are given by y1 minus y1, the estimate of that point. So if I want to get the residual of this, I would do my y1 minus my y estimate, basically, which you could say, so my y is 64 minus the estimate, which is 66.198. So let's do that. 64 minus 66.198. And this would equal negative 2.198. Now you're like, why is this negative? Why is the error negative? Because if the point is under the line, it will give me negative. And if the point is above the line, it will give me positive. And so don't overcomplicate it. That's really all there is to it. So that's really residuals. Now here we go a little bit more into residuals. We get a little bit fancy. We have error sum of squares denoted by SSE, which is just sum of squares error. That kind of sounds weird, but that's what it looks like to me. Which is basically the sum of all the errors. Okay, so I take all the errors between every point, like all this little distance here, all this little distance here, and I get the sum of squares for them. And then I also have the total sum of squares. And this one, I get the distance between my off and my mean. So remember, if I have like a graph that's like this, okay, your mean is some point here, and then you want to see how far each point is from the mean value, right? Well, let's say the mean is not here. Let me make a more horizontal graph. Like, let's say I have a scatter plot that's like, okay, well, it looks something like this, let's say. And you see, like, the mean the mean is probably like somewhere here where most of the data is. And so SSE basically takes all the distances between your data and the mean instead of the errors. Okay, so that's basically the difference. This one gets you the sum of all the errors. Errors. That sounds weird. And this one basically gets you how off you are from the mean, like how far you are from the mean. And so, what was I gonna say? Oh, I was gonna actually skip ahead to the coefficient, but we'll save it. To calculate SSE and SSD, obviously, you don't want to just keep adding each point up. And so you'll do this one for SSD. SSD is SSY, so okay, it's the same. So if you find your SSY, that's your SSD. Basically, you get this from your calculator. You get this from your calculator. Don't forget, this is different than this. This is the number you get from your calculator. This is a number you get from your calculator. Then you square that number, okay? And your SSE is basically just your SSD minus your BSXY. There's two ways to get it. This is also on the formula sheet, so you don't gotta worry about it. You can, so for your B, if you go up here to getting your B, this is the equation. So if you have your B, use it. If you don't, then you're gonna have to do a little bit of a harder one, because obviously you'll have to do your, what is it, XY over SXX, which is even more work. So if you have B, use it. Okay? But if you don't, you can always sub it in, or we'll find B, I guess. The reason this is SSY and SSD is because we said earlier here SYY does equal SSD. Now the coefficient of determination. This one, basically what we do is we take all the distance, all the errors in the graph or in the plot or in our data, and then we divide it by how far each one is from the mean, and that will give us a certain percentage. That will give us some percentage. And that percentage basically tells us which ones are explained by the data and which ones are not explained by the data. Now, this might sound a little bit gibberish to you, but let's go back up here. SSE gives you the errors, okay? And SSD, because it measures from the mean, it gives you the spread, how spread out your data is, okay? So like, you know, if I have a graph, I've drawn so many graphs now. I don't even need like the line of best fit, but if your data is like very spread out, that's what your SSD is. And so the smaller your SSD is, the more closer together your data is. It means it's more accurate. Like whatever you're doing it right. And then your SSE, if your SSD is small, but your errors are very large, that means there's something up with your line of best fit. There's a lot of things not explained, or there's a lot of outliers, let's say. So keep that in mind. SSE gives you errors, SSD gives you spread. So when I take the errors and I divide it by how spread my graph is or my data is, then it will tell me how many points are reasonable, aka explained, and how many points are not explained. It means they're unreasonable, aka, or you can also think like outliers. And so when I do this, this will give me unexplained. Okay? However, because I do 1 minus whatever this percentage is, it will give me explained. Okay? Oh god. I think my gum expired in my mouth. You know when you chew on a gum so much, it becomes so loose, it's like you're fucking chewing on food? Ew. Okay, so to use inner regression to measure how well the least squares line fits, basically, yeah, you're telling you like, if your data, dude, so many graphs. If your data is like, let's say this is your line and your data is all here, that means your data fits very well and your R is going to be very close to 0. Is it 0? I think the closer it is to 1. Yeah. So you want to go to 1. So if your R goes to 1, it means 100% of your data is explained. Remember, your R tells you you're explained. So if it's 1, it means 100% of your data is explained, which means everything is on the line, you're doing great. And the more towards 0 you go, it's the more your data is like unrelated. You know, like you have your data very spread out like this. and then you have your, line somewhere there. So that's basically what coefficient of determination is. Residual plot. This one is basically you have number 0 and you have your errors. So that's why they do. You have some x value, and then you get your error, which you take the estimated. Remember, this is the estimated, and this is the actual value. So you'll take the actual value minus the estimated. You'll plot it. Actual value minus estimated. Plot it, and then you keep doing that, and it looks something like this. And what you want it to be is you want the line to be at 0. That's what you're trying to aim for. Because if the line is then at 0, it means you have a lot of errors. So this is basically what we're doing up here. Where is it? This is basically what we're doing up here, except it's graphed. So you can kind of visualize your errors. All right. So to recap this lecture, this one, all I told you was that there is another equation that you can find your B and R. Here we spoke about, where is it? Yeah, here we spoke about residuals and the differences, errors in your data. Here we basically explained, we said SSE is the errors you get from plugging in a point, the sum of errors, you can think about it. SSD gives you how spread out your data is. And if you divide your errors by the spread of your data, it will tell you how unexplained, the percentage of unexplained data. Okay? And then if you minus that from 1, it flips. So it'll give you the explained data. Right? So if you have, 10% unexplained, and I do 100% minus 10%, I'll get 90%. And that's my explained data. So that's basically what we're doing with the R squared. That's about it. So we're done now with all this. We're going to go into sets next lecture, and I hope you guys found this helpful.